So DOM module 5, damped free vibrations. Damping is the resistance offered by a body to the motion of a vibrating system. The resistance may be applied by a liquid or solid internally or externally. Because of this resistance, vibrations die out over a few cycles of motions. So damping is a resistance. It is a resistance offered by a body to the motion of a vibrating system. The resistance may be applied through liquid, solid, internally or externally. Because of the resistance, vibrations die out in a few number of cycles of motion. Different types of damping. First one, viscous damping. Second one, column damping. Third one, or also called as dry friction. Third one, solid or structural damping. Fourth one, slip or interfacial damping. So in this, viscous damping is one of the common types of damping when system is allowed. It's a common type of damping when a system is allowed to vibrate in a liquid or viscous medium. The damping is called as viscous damping. The resistance offered experiences in various viscous damping is proportional to the velocity. That is, force is proportional to the velocity. Damping force is proportional to the velocity, or damping force is equals to C into V, where or F is C into x dot, where C is the damping constant. Differential equation of damped free vibration. I guess with different figure, a spring mass system with a damper of mass m with spring stiffness k and damping constant c is elongated by delta to a static position from the mean position after time t. It is being displaced by at x distance. Then the following forces acts on the body as shown on the right: kx mx double dot c stat. So in this, let k equals to stiffness of the spring, that is mg by delta. C is the damping coefficient. Omega is the frequency of damped free vibrations. X is the displacement of mass at time t. X dot is the velocity of the mass. X double dot is the acceleration of the mass. K is the spring force. Kx is the free spring force. Mx double dot is the acceleration force. Cx dot is the damping force. M is the mass. W is the weight. Delta is static deflection. Let the body is displayed by distance x in downward direction. Now the forces acting on the body are: first one, accelerating force, here as you can see from the figure, in direction of motion, that is mx double dot. M d square x dt square equals to mx double dot. Second is the damping force opposite to the direction of motion, that is cx dot. Third is the spring force, which is opposite to the direction of motion, that is also is kx. Now for dynamic equilibrium of the body, the sum of inertia forces and external forces in any direction should be 0. Therefore equation of motion should be, it can be written as mx double dot plus cx dot plus kx equals to 0, equation number 1. Or taking ms common, x double dot plus c by mx dot plus k by mx equals to 0, that is equation number 2. If c equals to 0, it becomes undamped equation. So then the equation can be written as x double dot k by mx equals to 0. So this equation for undamped vibrations. So now to determine the critical damping coefficient, equation 2 is differential equation of second order, assuming the equation in the form x equals to e raised to alpha t, equation number 3, and x dot is alpha e raised to alpha t, x double dot is alpha square e raised to alpha t. Substituting equation 2, we have alpha square e raised to alpha t plus c by m alpha e raised to alpha t plus k by m e raised to alpha t equals to 0. Now taking the e raised to alpha t as common, we have a square alpha square plus c by m alpha plus k by m equals to 0. So equating e raised to alpha t to the other side, we have a square alpha square plus c by m alpha plus k by m equals to 0. Equation number 4. Roots of these equations are alpha equals to minus c by m plus or minus square root of c by m the whole square minus 4 into k by m into 1, or 1 by 2 into minus c by m plus or minus square root of c by m the whole square minus 4 into k by m bracket close, or any of the alpha 1 alpha 2 roots are minus c by m 2m plus square root and c by 2m whole square plus k by minus k by m. Alpha 2 is minus c by 2m minus of square root of minus c by 2m the whole square minus k by m. Equation number 5. So equation number 5 takes equation number 6 takes 3 forms depending on whether c by m square minus k by m is 0, positive, negative. If 0, then c by m 2 square is k by m. C by 2m is root of k by m equals to omega n, or c is 2m omega n. The critical damping coefficient Cc is defined as the value of damping coefficient for c by m 2 by m was minus k by equals to 0. So critical damping coefficient Cc is 2m omega n, or 2 root mk. The ratio of damping coefficient to critical damping coefficient is called damping factor or damping ratio. It is denoted by zeta. The damping factor zeta is c by cc. Alpha 1 is minus zeta plus square root of zeta square minus 1 omega n. Alpha 2 is minus zeta minus square root of zeta square minus 1 and omega n. The most general equation, differential equation 2, is x equals to a1 e raised to alpha 1 t plus e2 e raised to alpha 2 t, or a1 e minus zeta plus square root of zeta square minus 1 omega n t plus e2 e minus zeta minus square root of zeta square minus 1 omega n t. Equation number 7. If zeta is less than 1, greater than 1, then the roots are real and negative, so it's called the overdamping. If zeta is equals to 1, then the roots are real and equal, it's critical damping. If the zeta is less than 1, then the roots are imaginary and both the roots are complex under damping.